Hello there, fellow electronics lover. In today's video, I'll be talking about PWM, pulse width modulation. We're gonna answer questions such as what is PWM, how does it work, and why is it at all important? So first, we need to understand what PWM really is. Well, it's in its name really, pulse width modulation. Let's put it this way. You have a pulse and it has a given width. Now, if you modulate that width, you have achieved pulse width modulation. Okay, that might have been a little bit too fast, but trust me, I'm gonna get into way more detail further on. Alright, now that we know the absolute basics, we can move on to our next and the best part of the video and answer the question of how does PWM actually work? Or in other words, how to make a PWM circuit. There is going to be multiple stages of the circuit. First, the oscillator, then the differentiator, which is just a simple capacitor and resistor discharge circuit. Then comes something called the ramp generator. And last but not least, the comparator, where we get a nice little PWM signal. Let's look at the oscillator stage first. It's the simplest 555 timer square wave generator circuit. This is how it looks. You have a couple resistors and capacitors to fine-tune the frequency of the square wave, or in other words, the pulse we talked about earlier. In my circuit, I wired up two capacitors in parallel at the threshold pin of the 555 timer, with a combined capacitance of about 45 nanofarads, and two resistors at the discharge pin with a combined value of 400 ohms. These values give me a stable 25 kHz square wave at the output of the oscillator, which is higher than audible frequency for humans, but also low enough to not have issues with transistor switching losses. Let's see how it looks like on the breadboard. There is our 25 kHz square wave signal on the oscilloscope. Now, let's put the differentiator together. It's a very simple circuit, but it needs quite precise values to work well. You see, I used the 10 nanofarad capacitor with a 45 ohm resistor, which is good enough for 25 kHz, but isn't for other frequencies. The point of this differentiator is to make the waveform spiky instead of square-like. If you don't understand the reason why, then I will explain it in a minute. Let's move on to our next segment, the ramp generator. It basically makes this sawtooth or triangle or ramp-like waveform. This is the most important thing in PWM. The ramp generator in my circuit is simply a transistor, a couple capacitors, and a resistor. But again, the values are needed to be quite precise to get a good sawtooth waveform. A good sawtooth waveform swings from ground, in other words 0, all the way up to 5 or 12 or however many volts you'd like. And on the way up, it forms a perfectly linear path before suddenly collapsing back to zero. Has a minimal time between cycles, and that minimal time sets the minimum duty cycle of the PWM signal. The working principle of the sawtooth generator is simple. There is a resistor which feeds current into the capacitor, which charges it linearly, then is connected in parallel to the transistor, which is connected to ground. So when the transistor conducts, the capacitor gets discharged, and here comes the spiky waveform from earlier. We need that waveform to go into the base of the discharging transistor. The reason that it needs to be spiky is to only discharge the capacitor momentarily. If it isn't spiky, the transistor will keep the capacitor discharged, thus not having a smooth sawtooth. And there you have it. The sawtooth waveform is done. Moving on now to the last segment, the comparator stage, where we will need a voltage divider consisting of multiple resistors with precise values to drop the voltage from 5 down to 3. The reason for it is the maximum amplitude of my sawtooth is 3 volts. So then I use the potentiometer to regulate that voltage from 0 to 3 volts. Now here comes the comparator. Feeding the sawtooth into the inverting input and the potentiometer output into the non-inverting side of the comparator, and putting a resistor from 5 volt to the output of the comparator to act as a pull-up resistor. And we have successfully achieved pulse width modulation. PWM is one of the most efficient things in electronics. It's almost everywhere. It's in your phone charger. Matter of fact, it's in your phone. It's in your computer. It is in certain lamps, and basically every single power supply. Speaking of power supplies, if you like this video, I am sure that you will like my next video that's coming out soon about power supplies. Make sure to watch it when it comes out. I hope you guys enjoyed the video and maybe even learned something from my horrible explanation. And since I'm pretty new in making videos, I would be happy to get some feedback. Alright now, bye fellow electronics lover.